This video is going to cover parts of Chapter 5, parts of Chapter 9, and parts of Chapter 10. Specifically, we're going to be talking about the normal force, the frictional forces, and there are two flavors of that, and torque. And then we're going to talk about the introduction to Chapter 10, which is another segment on equilibrium, and it involves the full equilibrium conditions. The first concept I want to introduce has to do with what's called the normal force. So the idea behind the normal force is the book has some weight, which in this case is 10 newtons, and it is pushing down on the surface with that force. In order for the equilibrium condition to hold, for the sum of the forces to be equal to 0, there must be some force in opposition to that created by the electrical interaction between the molecules on the bottom of the book and the molecules on the top of the table. This is not an action-reaction pair, even though they do in fact have equal magnitudes and point in an opposite direction. The frictional force we're going to introduce in the following way. Assume this book is still in equilibrium, and we push on it with our finger, and we call that force P. Latin or Italian, depending on how you want to look at the origin of using the letter P for that. So we're pushing the book towards the right with this force P. The book is being pressed against the table, and the table is pressing up against the book with a normal force, in this picture labeled with a big N. Sometimes the Greek letter eta is used, depending on what source you're using from a textbook or online. The S here is the net force of the book on the table. W is the weight, the force of the earth on the book, which is pointing downwards and is balanced by N. And that leaves us with this little force down here, F, which is a horizontal force between the book and the table, which is, in this picture, because it's in equilibrium, must be balancing P. So, this is where Chapter 5, Section 1 comes into play, and we start looking at frictional forces and how they are calculated. This diagram on the top shows the book in equilibrium, and the force F, as it does in the previous picture, points leftward in order to counteract the push to the right. A larger push to the right creates a larger force to the left in order to balance it. So up to the point where the book slides and is no longer in equilibrium, right, that's what's going on here, is that the sum of the forces is equal to 0. So the magnitude of this force changes depending on the magnitude of the applied push. Down here at the bottom, the book starts to move. It starts to slide across the surface of the desk. And at that point, the force P, the push, or the force from the finger, is greater than the frictional force that acts on the book from the table, causing the book to accelerate, and in this case, the sum of the forces is greater than 0. It is also possible, now that the book is moving, for it to move at a constant velocity, which, from Newton's first law, is a new equilibrium condition. The forces are again equal to 0. The forces aren't equal to 0. The net force is equal to 0. And in this case, again, P is equal to F. This case on top is what we call static. And it's in static equilibrium. In other words, it's not moving. In this case, the book is not in equilibrium at all, it is accelerating. And once it is moving at constant velocity, case E, that's what we call dynamic equilibrium. Just as a quick aside, since it's taking me so long to write this, I am looking for better software so that I can both write faster and maybe even a little more neatly. Static equilibrium, acceleration, dynamic equilibrium. The frictional forces come in two flavors. The static friction comes into play, or is created, when the surfaces remain at rest with respect to each other. So in that case, the static frictional force is equal to the applied force, and the object remains stationary. And the formula for that is this: F max, sometimes Fs max, is equal to mu s times n, where mu is the so-called coefficient of static friction, and it is a property of the two surfaces, and a property of the interaction between the two surfaces. So there are some standard values for surfaces that are fairly standardized, but for the most part, it varies according to individuals, so you have to determine that experimentally. Contrast that with kinetic forces, where the surfaces are in motion with respect to each other. And in that case, the kinetic frictional force, sometimes written Fk, is equal to mu k, the coefficient of kinetic friction, times the normal force. Static friction, mu s, and kinetic friction, mu k. And I want to emphasize this. Friction opposes relative motion, not absolute motion, independent of the fact that there is no such thing as absolute motion. What is being opposed is the motion between the two surfaces. So if you go to the grocery store and you're checking out and you place an object on the conveyor belt, the conveyor belt is not moving with respect to the object that you have set on the conveyor belt. So your static friction is actually causing the object to move with respect to you, because it's maintaining rest with respect to the surface that it's sitting on. Think of a box in the back of a pickup truck. Most of the time you're driving around with a box in the back of your pickup truck, it's moving at the same speed as the truck. So the box is at rest with respect to the bottom of the truck. Static case. It becomes kinetic when you slam on the brakes, and that static frictional force is no longer large enough, and the box slides to the front. So remember, what you're always looking for in terms of friction is relative motion between the